world. My name is Alice.
And my name is Brendan.
We are doing our fourth year electrical engineering project on machine learning for optical mode detection. Laser beams can have different cross-sectional shapes and wavefronts. These different shapes are known as optical modes. Their advantage is that many of them can be sent at the same time without them affecting one another, which is not possible with other shapes. Although mixing the two modes changes the shape of the beam, the original beams can be determined from this final beam. To make use of optical modes, we need to find a way to quickly differentiate between them. This can be done using machine learning. However, machine learning on the beam shapes alone cannot differentiate between all modes, as can be seen here. These are pictures of two different modes. However, they can be differentiated using the different wavefronts of the beams. The only way wavefronts can be seen on a camera is if interference patterns similar to those shown in the final two pictures are produced. Interference patterns are created when a mode and a normal Gaussian beam intersect using a Mach-Zehnder interferometer, which has been included in the optical setup. The optical setup, as seen here, begins with a laser diode that produces a laser beam. This laser beam is split into two parts at the pellicle. The first part is converted into a mode by a digital micromirror device, and the beam mode propagates to the beam splitter. The second part is required to act as a normal Gaussian beam when the interference patterns are produced at the beam splitter. The camera is used to take the images of the beam.
For machine learning, we used convolutional neural networks with different sizes and compared the accuracies between intensity and interference inputs. For practical applications, we also considered both resolution and noise performance. Noise is caused by laser beams being affected by the turbulence in the air. This is also why the stars twinkle at night. Ooh. Here we see how the laser beams change with turbulence, which we simulate to test the effectiveness of neural networks. Now let's take a look at resolution. Lower resolution cameras are cheaper and faster, but as you can see, the image quality loses details with the lower resolution, which will then affect the neural network's performance. So how well does interference perform compared to just intensity? Well, as you can see in the graph, it performs better for all resolutions. We have an average improvement of 20% in accuracy from the medium to high turbulence levels. Okay, so that concludes our presentation.
Hope you didn't fall asleep.
Well, I would have.